What if the first evidence of life beyond Earth doesn't come from NASA, but from a Chinese drill boring 2 meters into Mars? Tianwen-3's subsurface mission is designed to bypass the planet's radiation-baked surface, reaching untouched layers that could still contain organic molecules. But how exactly does this mission plan to do that without a rover? And why does that decision make success more likely? Stay tuned to see why scientists believe this buried material could hold the Martian secrets the world's been chasing for decades. But before we dive in, please hit subscribe and like the video. Your support means the world to us. It helps us grow the community and bring you even more exciting space discovery videos. Thanks a lot. And now let's dive in. Every Mars rover so far has searched the surface, but what if the real evidence of life lies just 2 meters deeper? The surface of Mars has been through an endless chemical assault. For billions of years, it has been exposed to streams of cosmic radiation and bursts of charged particles from the Sun. The planet's thin atmosphere offers almost no protection, so every incoming particle penetrates the dusty crust and alters whatever molecules it meets. Oxygen-based compounds like perchlorates, which are abundant in Martian soil, react aggressively with carbon-based materials. The result is a surface that constantly destroys the very chemistry needed to confirm life, whether long dead or possibly dormant. That helps explain why even the most advanced rovers, Curiosity and Perseverance, find only traces of organic matter. When they heat their samples for analysis, much of what could have once been complex carbon molecules breaks down into simpler fragments. Those fragments are like chemical fossils, enigmatic, incomplete, and hard to interpret. The problem isn't the skill of the instruments, it's that they are working with material already damaged. Solar ultraviolet light pounds the surface daily, and high-energy cosmic rays dive deep enough to disrupt molecular bonds. Over geological time, these two factors combine to erase or distort organic signatures, leaving behind only the faintest chemical clues. 2 meters underground, conditions change dramatically. Shielded by layers of dust and rock, organic molecules can survive without being constantly struck by radiation or scorched by oxidizing reactions. The deeper soil acts like a protective archive, freezing in place chemical and isotopic patterns from Mars' wetter past. Some scientists describe that buried zone as an ancient time capsule, one that could preserve the record of a world that once hosted rivers, lakes, and even a thicker atmosphere. That is why Tianwen-3's 2-meter drill depth matters so much. It's not just going under the surface, it's entering a region that has been geochemically stable for billions of years. The idea has strong support from what we've seen on Earth. In Antarctica, organic remains have survived for millennia, locked inside permafrost, isolated from air and reactive compounds. Even microbes have been revived from those icy sediments after being trapped for tens of thousands of years. The same preservation logic applies to lunar regolith that guards solar wind particles untouched by human contamination. On Mars, the subsurface may play the same role, protecting whatever molecular evidence was sealed back when the planet still had water flowing on its surface. Now here's where the story turns interesting. Tianwen-3 won't roam across mountains or craters searching for ideal drill spots. It's a stationary lander. At first, that sounds like a disadvantage compared to NASA's mobile rovers, but that fixed position brings an unexpected benefit. Without the need to travel, engineers can build a more robust and deeper drilling system, one capable of reaching below the oxidized layer and into pristine material. Each drilling operation can focus on contamination control, preventing Earth microbes or Martian dust from mingling with the samples. That means what comes up from the drill could represent the first truly untouched soil humans have ever seen from Mars' protected subsurface. Extracting that core could answer a question scientists have chased for decades. What really happened to the organic chemistry that once thrived on early Mars? Did it vanish completely, or did it simply retreat below the reach of radiation, waiting for the right robot to dig it up? Tianwen-3's methodology leans into that mystery. The lack of a rover simplifies its design and enables more precise, cleaner drilling. What began as a limitation is, in fact, its critical strength, the ability to dig deeper, cleaner, and possibly sooner than any mission before it. And this fixed approach sets the stage for how China plans to turn its stationary lander into something far more powerful than a simple drill. A mission without a rover sounds like a handicap, so how can Tianwen-3 still sample more effectively than NASA's billion-dollar rovers? The short answer is that every part of its design focuses on removing complexity. Instead of spreading its technology across several missions, China built Tianwen-3 as a two-launch system that works together as a single machine. One spacecraft will send the lander and ascent vehicle to Mars, while another will orbit the planet waiting to bring the samples home. The schedule spans almost a decade from planning to Earth return, with a 7 to 8 month cruise to Mars, about a year of surface operations, and a 3-year total mission time. It's an ambitious but tightly coordinated setup aimed at one goal: retrieve untouched Martian soil. The lander itself carries the drill that will reach 2 meters into the ground. That depth is not random. It strikes a balance between engineering practicality and scientific value. Below that point, samples are better shielded from radiation and oxidation. The drill will extract cylindrical cores, each carefully measured and transferred into airtight tubes. A robotic arm will control the handoff to avoid contamination from dust or the lander's structure. As soon as a core is sealed, the container's internal atmosphere will be locked, preserving any volatile gases or organic signatures inside. Even temperature fluctuations are accounted for. Small insulation layers and vacuum seals help maintain the sample's condition during storage and ascent. Of course, a stationary lander raises an obvious issue. One location doesn't represent all of Mars. That's where Tianwen-3 introduces an unexpected tool: a small drone capable of flying several hundred meters from the main platform. This aerial scout borrows lessons from NASA's Ingenuity helicopter, but is designed for short, controlled hops. It will carry lightweight instruments and possibly collect surface dust or small rock samples from nearby spots before returning to the lander. This approach expands the sampling zone far beyond a single drilling point, giving scientists a range of materials within just a few hundred meters. Each piece offers layered information: wind-blown dust, surface crusts, and the precious underground cores. Once all samples are ready, the lander transfers them into the Mars Ascent Vehicle. This small rocket is already attached, minimizing moving parts or external handling. When the time comes, it will launch a metallic capsule containing at least 0.5 kilogram of Martian material into Mars orbit. There, the waiting orbiter retrieves the capsule with autonomous precision and prepares for the journey back to Earth. No human oversight guides this in real time. Communication delays mean the entire encounter must be automated. The coordination between ascent and orbiting stages is one of the mission's technological highlights, each movement pre-programmed yet flexible enough to handle Mars' unpredictable conditions. Every step follows strict planetary protection rules based on global standards set by the Committee on Space Research. On Mars, that means using sterilized tools and minimizing how much terrestrial material touches the soil. On Earth, it means the returned capsule will never be opened outside of controlled facilities. China is already constructing a dedicated biocontainment laboratory near the Hefei Institute of Physical Sciences for that purpose. Inside, scientists will handle and test the samples under ultra-clean and sealed conditions designed to prevent cross-contamination. These safety measures protect both scientific integrity and Earth's biosphere. NASA's plan, by contrast, relies on a multi-stage campaign involving several vehicles and handoffs before a return capsule even leaves Mars. Tianwen-3 bypasses that chain entirely. By drilling, sealing, launching, and recovering samples within one unified operation, it avoids years of additional coordination and cost. If nothing delays it, those sealed cores could arrive on Earth years before NASA's cached samples ever leave Mars. The prospect of China delivering the first authentic Martian soil isn't just symbolic, it could redefine whose instruments first test evidence that's been untouched by radiation, wind, or time. And that raises a bigger question than competition alone. What if the first proof of alien chemistry comes from this quiet, fixed machine operating in the red planet's stillness? If Tianwen-3 succeeds, Earth's first untouched Martian samples may come not from NASA's Delta deposits, but from deep, sealed soil selected for it to preserve biosignatures. These samples could carry chemical traces shielded for billions of years beneath the planet's harsh surface, offering the most authentic look at Mars' biological potential. Their discovery would mark more than a milestone. It would reveal how life might take root beyond Earth. The next great revelation about our universe might not depend on who reaches Mars first, but on who searched where sunlight has never reached, waiting for scientists everywhere to study together.